Hello, hello. All right, let's look at quantiles, also known as k-values. To begin, a recent recap. Go ahead and give this a try. Pause it now. All right, let's go ahead and have a conversation on this. All right, state the expected number of faulty helicopters in the sample. We're looking for E of X. So let me go over here. Let me make this slightly bigger so you guys can see that. All right, so remember, E of X, that's just mu, which is the same as the probability times N. So the probability of being faulty, 0.18 times 50, and we'd expect 9 there. All right, B, find the probability that 3 helicopters are faulty. Remember, this is a discrete variable. We can count this, so we're not in the continuous tool set. We're back into the discrete tool set, which is the binom PDFs or CDFs. If we want to equal in exactly 3, that's a binom PDF of 50 samples. 50 is our N, 0.18 is our P, and our X is 3, and there's what I got. All right, find the probability that more than 12 helicopters are faulty. So the probability X is greater than 12. Remember, your CDF function is not built for greater than, it's only built for less than. So I'm going to translate this into equals 1 minus, well, what do we want to take away? If we want to include everything greater than 12, for example, 13, 14, 15, and so forth, then we want to take away from the entire group 12, 11, 10, everything below that. So what I'm going to do is 1 minus binom CDF, again, it's MPX, and when I did that, I got about 0.102. So about a 10% chance of that happening. Okay, next one. Find the probability. Solve for the probability of X being between 4 and 10. Now remember, this being a discrete variable, it can't equal exactly 4, it can't equal exactly 10. So let's look at this. Here we are. So first off, since I can't equal 10 and wants to be less than 10, I actually have to build it as less than or equal to 9. Remember, your CDF function was just built with less than or equal to into it. So what we're going to do, I'm going to do the probability X is less than 9, which will tell me the probability of everything X is less than 10. The probability X is less than or equal to 9. So that's going to give me everything below, but now I want to take out for this piece, so now I'm going to subtract out the probability X is less than or equal to 4, because we do want to exclude 4, exclude 3, 2, 1, and 0. So we're doing the binom CDF. Is this binom CDF minus this binom CDF, and there's what you ought to get. All right, let's move on. Next, to review recent material, I wanted us to give this a shot. This would have been with pods. Go ahead and pause it, give this a try. All right, these topics are a bit newer for us, so I really hope you gave yourself a chance to practice, but let's dive in and review those. Okay. So suppose our variable x is normally distributed with a mean and a standard deviation. Let the z-score of this score be z1, and let the z-score for this score be z2. First off, calculate z1 and z2. Let's see here. All right. So that's right here. Quick reminder what our z equation is. Remember, this tells you the number of standard deviations from the mean. So it's your score minus your mu divided by standard deviation. Again, the number of standard deviations from the mean. Okay, so plugging our scores into this equation. Here's the first score minus our mean, all divided by standard deviation, and I get negative 0.86. So that means this score is negative 0.86 standard deviations below the mean. There's Z1. Let me underline that in red. Z2, same equation. Be careful. There's what I got. Okay, part 2, find the probability of Z being between these two values. So it's asking the probability of Z being between these two values. You might be stuck for a second. Well, what do I do from here? The big reminders is whenever you have Z, you know the mean, you know the standard deviation. Once you've transformed it into a z-score, your mean is 0 and your standard deviation is 1. I'll just write that just to make it real explicit. 0, standard deviation is 1. And so now you can plug this into your normal CDF. Okay, here. I actually have it in my normal PDF, sorry. with our variable, our mean, our standard deviation. Let me graph this. Oh, I have a graph there I don't want, so I'm going to go back. I'm going to turn off the equation, turn the equation back on. Let's try it now. Okay, so now we're going to find the area under the curve between, what were our two values here? Lower limit, negative 0.86. Upper limit, 1.183. Great, okay. And that's what you get. Part B, check your answer by directly calculating this from our calculator. So remember, for here, we can also go distributions, normal CDF to look at a range here. Lower bound is 50.6, 50.6, comma, upper bound, which is 68.9, comma, and then our mean, and then comma, our standard deviation, comma, 8.96. And hopefully we get the same answer. Awesome, we did. Okay, so there's direct calculation or the other way. All right, question 2. The average height of 17-year-old boys is normally distributed with a mean and a standard deviation. Calculate the percentage for these various ones. All right, more than 195. So more than 195 for this distribution. Now there's a handful of ways you can set this up. I can go back to our graph here, and for our mean I can put in a mean of 179, 179, and set our standard deviation is 8. Now if I'm doing it this way, I need to adjust my window. This window is going to be quite a bit bigger. This window has to go all the way up to 179, but several standard deviations beyond that. So I'm going to add about 40 to that. So I'm going to say 210 is my max. Let me say my max is 210. And my minimum, I don't know, I'm going to say 120. Remember, these are probabilities, so y between 0 and 1 makes a lot of sense. Let's have a quick look at this graph. Okay, so that's really low probabilities. I'm actually going to adjust my window. Rather than have my y max all the way up to 1, I'm going to set my y max to, let's say, 0.2. Maybe we can have a better look at this graph. Okay, so there we got a little bit of a nicer curve. Let's go ahead and find these probabilities. So more than 195 means 195 is my lower bound, and I just have to choose a really big upper bound. So let's go second calc, intersect. Our lower bound is 195, 195. Upper bound, I'm going to choose something relatively big. I know I set my max to 210, so I'm just going to say all the way up to the max. And there it's going to tell us 0.022, which is hopefully, oh, yeah, that is what I ended up getting here. Okay, you could also do this from your home screen if that way isn't working as well for you. I can go normal CDF. This time I'm going to put in my lower bound is right here. What is that? 163, 163. Delete that. And 195 for the next one. 195 there. Put in our mean. 179. And now our standard deviation of 8. Do it from our home screen. 0.954 and 0.954. Okay, great. And then for part C, do the exact same that we just did in the previous one, just with those values, and that's what you should get. All right, that was a lot. Let's move on. Okay, so for the standard normal, oh yeah, we just had another time on those ones, so nothing there. We've already gone over those. Quick recap. See if you can answer these on your own. What is the z equation? What is the z? And fill in the blanks. Pause for a second. Think through that. Okay, so first off, the z distribution, your z equation, you just used it, so it's probably in your head, but I'm hoping it can just really, you remember it. That is x minus mu over sigma. So it's the number of standard deviations from the mean, and that's what this one is. The number of standard deviations from the mean. Z is distributed normally with a mean of 1 and a standard deviation, sorry, a mean of 0 and a standard deviation of 1. I got ahead of myself there briefly. Okay, let's dive into quantiles. Here's kind of a context of this. So let's consider a population of adult monkeys where the weights are normally distributed with a mean of 60 pounds and a standard deviation of 13 pounds. Let's say we want to put the heaviest 25% on a vegetable-only diet for some reason. So we're trying to figure out what is the weight that the 25% heaviest are. So what we're looking at here is, from this one, what's the probability X is below some score? What score will equal 75%? Remember, for less than, all these graphs go to the left. If we're trying to find the upper 25%, well, that's connected to or the same as finding the bottom 75%. So as far as the title, quantiles, also known as k-values. I've always called them k-values, but quantiles is what IB was calling them. What we're looking at is how to solve for this value here if you're given the probability. So far, we've been given these and asked to find probabilities. We're going backwards. All right, so far before today, we've been given a mean, given a standard deviation, and asked to find probabilities. That's what you guys did in the warm-up. That's what you've been doing recently. Today we're going the other direction with an inverse operation. Always in math, if you go one direction, it's really nice to be able to go back the other direction. Okay, so follow me through these three examples. Let's look at this. Okay, so first we're given some mean and some standard deviation and a probability. How can we figure out what score correlates to 65%? Let's look at this. To get the ball rolling, I highly recommend you guys look at the graph, especially if this feels a little cloudy. Have a look at the graphs. All right, so here it's saying the probability X is less than or equal to some value, and it's 65%. So on the graph, that's what value on our bell curve, what value is 65% below or 0.65? This is the fundamental question. So here's the picture, looking for this score. Right off the bat, you might ask yourself, should this value, this k value, be above the mean or below the mean? It should definitely be above the mean because we're beyond 50%. Okay, you do have an inverse normal function on your calculator, which is so nice. Let's turn this on. I'm going to go second distributions, and it's the third one down. It's inverse normal. Now, inverse normal, the syntax for inverse normal, if your calculator doesn't tell it to you, it's the probability, which is just whatever this value is, and then your mean and your standard deviation. So to use this inverse normal function, put in the probability, 0.65, our mean, and our standard deviation, and here it spit out 10.77, and that is our k-value. Let me underline that in red. That's our answer. And that makes sense. If our mean is 10, our standard deviation is 2, and we're looking to just go 15 percentage points into this 34%, that makes sense. So 10.77 seems reasonable there. All right, let's look at part B. Find k such that we have 0.32. Let's draw that picture again. So here's what that picture looks like. Again, notice this is for less than or equal to. Less than or equal to means shade left. Shading left again, and this one was shaded left. So shading left here, we're looking for this k value. What score correlates to 32%? Okay, so similar to in the other one, we have our inverse normal operation. You have some probability, your mean, your standard deviation, and you get 9.06, and that is our k value there. So that's the score. All right, with 1 minute left, let's go ahead and do part C real quick. Part C, notice this is greater than. Greater than shades this direction. Your inverse normal function was not built for that. You cannot do this with the inverse normal function. We have to switch it. So if we're looking for 55% above, well, we could also switch that to a less than, looking for 45% below. So 0.45 here is what we're looking for. So then do the same thing, that inverse normal with 0.45, and you'll get this k value. All right, let me just show you these other things real quick before we run out of time. Here's the assignment, pause it. Here's the first set of questions. And the last two. I hope this all helped. Let me know if you guys have any questions. Take care.